The reason infrared radiation gets absorbed by organic molecules is because that's right in the frequency range that can cause bonds to vibrate in resonance. So just like you can start a guitar string vibrating if you hum the correct note right next to it, infrared radiation has just the right frequency that it can get bonds to start moving in and out or side to side, right? In and out movement is called stretching. Any side-to-side movement is called bending. So bond vibrations happen at the same frequencies of certain infrared wavelengths. Slightly different bonds will resonate at slightly different frequencies, but those frequencies are characteristic of the bond. These frequencies are given in wave number. Recall that frequency, Greek letter nu, frequency is speed of light divided by the wavelength. So frequency and wavelength are inversely proportional. Nu bar, right there, is called wave number. That's the unit we use. It's in inverse centimeters or reciprocal centimeters. Reciprocal, as they're called very often. And all that is just the reciprocal of a wavelength in centimeters. And the reason we do that is to just simplify reporting on the spectra. The correct frequency range is between 800 and 4,000 reciprocal centimeters. So rather than dealing in tiny little units or powers of 10 or something like that, the wave number is not exactly a frequency. Okay? It's proportional to frequency in hertz or some unit like that, but it's not an actual frequency. It's related, but a lot of times, just to be quick, we call it frequency because it's good to think of it that way. The way that these bonds vibrate, stronger bonds and lighter atoms, those both resonate at higher frequencies. A strong bond would be like the difference between a very strong spring, like a car suspension spring, versus a slinky. A strong spring will vibrate very quickly if you hit it, right? Or if you hold it and you shake it up and down like that. See? Imagine a large, very strong spring versus a slinky, right? And the up and down type of vibration will happen very quickly. With a rigid spring, it'll go very slowly with a slinky, right? You pull it down, it'll go up and down and so on. So the weakest bond, right? I don't know why my triple bond didn't show up here. It's supposed to be a triple bond. The weakest CC single bond would be like a slinky. It vibrates very slowly. Add a double bond, right? Starts going a little faster. Triple bond, faster yet. Going from single to double to triple is strengthening that bond because we have extra electrons being shared in between them. So stronger bonds vibrate faster. Then, if we have smaller atoms, those vibrate much faster yet. So it's just because of inertia that large things tend to vibrate slower than small things. So if I have a CH, it's a single bond, okay? But it's going to vibrate much more quickly, right? Since these reciprocal centimeters are proportional to frequency, this 3,000 reciprocal centimeters is a faster vibration than 21 or 16 or 1,000 that way. So keep that in mind, that anything with H, any kind of bond to hydrogen, will be vibrating much more quickly than any bonds between two larger atoms.